Okay, so have a look at page 25. All right. So this one is November 17, P41. So state by reference to simple harmonic motion, what is meant by angular frequency? This one is something that you can just get from your notes. Angular frequency is just frequency expressed in terms of radians per second. Or if you wanted to, you can actually just write out your equation omega equals to 2 pi f in words. Okay, where you say that angular frequency is equals to 2 pi times frequency. All right. In your marking scheme, you are allowed to write out your equation, but they must be in words. Right? If you just write it in symbol form like this, omega equals to 2 pi f, this one is not accepted unless the symbols are defined specifically in the answer. Okay. So if that is all right, then you move on to B. So I'll clear off the things here. Okay, so in part B here, what they mention is that you have a thin metal strip that is clamped at one end, so that is horizontal. You have a load of mass capital M attached to its free end. This load causes a displacement S of the end of the strip as shown in this figure below here. So the load is displaced vertically and then released. The load oscillates. The variation of the acceleration A or the displacement S of the load is as shown in the figure below. Okay, so this is the graph shape that you get. All right, it's a straight line graph with negative gradient, but it looks a bit different than the one that you are supposed to expect. If you recall the defining equation for simple harmonic motion, let's just review it a little. We said that A is equals to negative omega square x, such that if you were to compare with the equation of a straight line, the y-axis would be acceleration, the x-axis would be your displacement, and your gradient would be your negative angular frequency squared. So this graph, this equation itself would tell you that you should get a straight line graph through origin with negative gradient. So that if you want to draw it out now, it typically looks like this. So this one is your graph of A versus X. You expect to see something like this. Okay, a straight line graph to origin with negative gradient. So this is what you are always expecting to see, but somehow when you look at this question here, you will notice that yes, it is a straight line graph with negative gradient, but it doesn't seem to pass through origin in the first place. You see, this one here is passing through the origin, but the other one here, it doesn't seem to pass through origin. Okay, so the reason for that is because this is not really your displacement time graph that you expect to see. All right, so in the first place, what you can actually see here is that your y-axis is A, but your x-axis is displacement. But in your current question, it's the other way around. Your y-axis is displacement, your x-axis is your acceleration. The axes here are actually reversed in the first place for this question. Okay, but that still doesn't explain to you why isn't your graph starting from the origin, like what you expect. Okay, now this one, you have to firstly look at how your displacement S of your load is defined here. Okay, so if you read back the question earlier, they told you that your thin metal strip was originally horizontal. And then after you attach a mass M here to the free end, it causes the displacement S of the end of the strip here. So you could say that this one was your unloaded position. And then after you attach the mass, it went down, and you measure the displacement. The displacement S here that you see is actually measured from the unloaded position. Or you can think of it as from the unloaded horizontal position. Okay, this is how you measure your S here inside your question here in the first place. The displacement that you always use for A equals to negative omega square x is displacement, that's correct, but it's always displacement measured from equilibrium. So this is one key thing that you need to always be mindful about. This one is displacement measured from equilibrium. Okay, so this x that you have here and this s that you have here are not exactly the same thing, in the sense that they are actually not measured from the same reference point. The x in your equation here is supposed to be measured from equilibrium, but the s that you have in your question is not measured from equilibrium, but rather from the unloaded horizontal position. Okay, so that's one thing to note here. So this part here, where your object suddenly move down with you attention and load mass m here, at this position here, this one is considered to be your equilibrium position already. They then mentioned that after that, your load is displaced vertically and then released, right? And then your load oscillates. This means that after this, your load, it just oscillates up and down like this. This one here can be considered as, say, your top position. This part here can be considered as your bottom position. And needless to say, where you are here right now, this is considered to be your equilibrium. This is how you're supposed to measure your displacement x from your equilibrium position. Okay, so just so you know what's the difference between this graph and the graphs that you're always expecting to see, right? So the object is oscillating with simple harmonic motion, and this is the graph that you get. Okay, it's not the usual graph that you expect to see, but you can still work some things out of it. Now you move on to the actual part of your question, where they now ask you, use the figure that you have to determine the displacement of the load before it's made to oscillate. Okay, what is the displacement of the load before it's made to oscillate? This one is actually referring to the equilibrium position. Let me just try and word it out here. If they say to you to find out the displacement of the load from unloaded position, the displacement here that they're talking about is from the unloaded position before it's made to oscillate. This one is actually talking about it at equilibrium position. Okay, so if you look back at your graph, where do you suppose is your equilibrium position? This part here could be your equilibrium. This part here is your equilibrium. Okay, how do I know this? Is because my acceleration is 0. If you look back at the equation, A equals to negative omega square x, A is 0 when x is 0. In other words, at equilibrium. Because A is proportional to x, A is 0 at equilibrium, meaning to say x is 0. But A is max at amplitude, meaning to say x is x0. Okay, this is just one thing to note. All right, so if you look at your graph right now, your x-axis here is actually representing your acceleration. So look at the part where your acceleration is 0. This part here is the part where your acceleration is 0. So you read off the value of displacement which has 0 acceleration. That is the displacement that you want. This is the displacement of your load when you are at equilibrium position right now. It's 2 centimeter. Okay, so that's for that part. It is at 2 centimeter. Then the next part of the question requires you to find out the amplitude of oscillations of the load. If you already found out the equilibrium position, what is the amplitude of the oscillations of the load now? So this one, when you look at your graph here, simple logic would tell you that your amplitude position is really going to be at the end of your line there. This parts that you see here is really your amplitude position. So this one here is actually your bottom position. Let me write it out. This one is actually your bottom amplitude. Whereas this one here is actually your top amplitude. How do I know this? Is because your S is measured from the unloaded position. If this one is your equilibrium, and this one is your bottom, and this one is, say, your top value would always be lesser than the bottom value, because this one, let's just say, is the length at the top. Okay, the displacement at the top. Let's just call this displacement at your top, and then let's just call this displacement at your bottom. Your displacement at the bottom will always be larger than the displacement for the top. So you can actually see from this one here, this one here is actually going to be amplitude, but it's actually the lowest value is actually U or mass at the top. And then this one here is also your amplitude position, but the displacement is the largest from the unloaded position. This is going to be at the bottom. Okay, that's just one thing to note, right? But the gist is that you should be able to identify that this point is where you are at amplitude position. Okay, so right now you want to find the exact value of your amplitude itself. To find the exact value of your amplitude, you just take the difference between these two lines. Because displacement is always measured from equilibrium, this one is your amplitude. This one will also be your amplitude. Okay, this one is probably 3.5 minus 2, giving you 1.5 centimeter. Whereas this one is probably 2 minus 0.5, giving you 1.5 centimeter. Okay, so regardless of which one you use, you should get the same amplitude value. It will be 1.5 centimeter. So when you want to explain something is undergoing simple harmonic motion, you can actually explain it from a graph shape. For the ones that you have here, the typical graph shape of acceleration versus displacement, if you want to explain from this graph, that is simple harmonic, what you would have actually say is that if it's a straight line graph through origin, it tells you that A is proportional to X. And then the second thing here is that you have a negative gradient. So it tells you that A and X are always opposite direction. So when you have this one and this one, A and X are always opposite direction. A is directly proportional to X. Therefore, you would have simple harmonic motion. Okay, A and X are always in opposite direction. So if you wanted to explain from the graph, usually you need to have these 2 points to prove that it's simple harmonic motion. So you are going to use that same similar points here for your graph. But as I mentioned to you earlier, your graph isn't your typical graph that you expect to see. It is a slightly different graph because your displacement is not measured from equilibrium, but rather from the unloaded horizontal position. So you will need to modify your points a little, and you need to add in some additional statement because this one is a 3-point question. Okay, so you can see that this and this is really probably just going to be 2 points. There must be some other additional point here. So the other additional point that you needed to say here is something to relate the graph that you have with this graph. Okay, so what you would have to say is this statement here, where you say that the graph shows the variation of acceleration with displacement of the load as it oscillates about the equilibrium position. You just write this one should be enough. You don't need to write at s equals to 2 centimeter. Okay, so this is where you get your 1 mark from. The other 2 mark is you taking these 2 statements here. All right, where you say now the straight line indicates that acceleration is directly proportional to displacement, and the negative gradient indicates that acceleration and displacement are always in opposite direction. This one is 1 mark, and this one is 1 mark. Okay, so specifically for the second sentence here, you say a straight line only. Okay, the one that I have here is straight line through origin. That is because I'm referring to this graph directly. But your current question graph is not a graph through origin. Okay, so you cannot simply say it's a straight line through origin. You saying just a straight line would be enough. Okay. Now, for the last part here, you are supposed to calculate out the frequency or oscillation of the load. Okay, so the one that I showed you here, this one is probably not a really good working to follow. There's actually an easier one to use. If you remember just now I told you, simple harmonic motion is always defined by this equation. A is equals to negative omega square x. So if you know that this equation is the one that always defines simple harmonic motion, to do this question here that you have, when you want to find out the frequency, you can use something called single point substitution. Use single point substitution method, where it means that you pick any point on graph to obtain a pair of A and X values. Okay, then after that you sub the values into the equation. Okay, all right. So if you want to use single point substitution method, all you just need to do is you just take a point on the graph to get you a pair of X and A and X values. From there, you just sub out the values into your equation to find your answer. So if you just look at your current question here, because I already know that this represents your object undergoing simple harmonic motion, so an easy thing that you could do is to pick any point on your graph to get a pair of A and X values. So to make your life simple, just now you actually already did find out your amplitude position. In my case, maybe I don't want to use amplitude position because it's hard for me to read. Say I want to pick any points here on my graph. Say right now, I want to pick this particular point. Okay, so if I pick this particular point here, over here, this one, the value that I should have for the displacement would be 3 centimeter. Sorry, the value I should have for the displacement is actually going to be 1 centimeter, because this one is my equilibrium position. So let me just try and write it down here for you. Because this one was my equilibrium position, if I pick this point here, my displacement x is really just going to be 3 minus 2, giving me 1 centimeter. And my acceleration is negative 0.6. Okay, so my A here is negative 0.6 meter per second square. So if I pick this point here, my displacement is 1 centimeter, my acceleration is negative 0.6 meters per second square. So all I just need to do from there is I substitute inside A equals to negative omega square x. A right now is negative 0.6 equals to negative omega. Because I wanted to find frequency, what you could do is that you substitute out omega so that it gives you frequency. If you recall what I mentioned to you before a lot of times, omega is 2 pi f or 2 pi over t. Okay, so right now you change it out to become 2 pi f. Don't forget to square it. Then sub in the value of your displacement of 1 centimeter. So this one is 0.01, change to meter. So your f eventually will give you this answer. Let me just try to calculate it out first. So it's 0.6 divided by 0.01 divided by 4 pi square root of your answer. You should be getting a frequency of 1.23 hertz. Yes, you will get the answer as 1.23 hertz. Okay, so you could pick this point here, or you could also pick your point at the amplitude position. All you just need to do is you make sure that you get the corresponding value of A as well as the corresponding value of your displacement. In my case, I already know that the displacement here is actually 1.5 centimeter because this is my amplitude. But I have to go and purposely read out what is my acceleration. But because it's somewhere in the middle of my square, it's a bit hard to read. So that's why I did not choose this one. You could have also chosen this point also. You will get back the same answer. Okay, you can choose the blue color point, you can choose the red color point, you can choose any point along the line. You will still get back the same answer. Okay, so this is what single point substitution method is. Just pick a point on the graph, sub it inside the equation, and you get the answer. All right. And there's another different method to this. This one is the one that is actually used by the marking scheme. This is actually you trying to equate it to y equals to mx plus c. So what we mean by that is something like this. I'll show you the method also. So what they essentially do here is that they say that A is equals to negative omega square x, and then they rearrange it such that x equals to negative 1 over omega square A, because they want to compare it to the equation of a straight line. Because you can see you have a straight line graph, isn't it? So because your y-axis is your displacement, and your x-axis is your acceleration, you have to rearrange your equation like this, so that your gradient is going to be negative 1 over omega square. So you could say that negative 1 over omega square is actually your gradient. 1 over omega square is your negative gradient. You find out your gradient, equate it to 1 over omega square, and then subsequently substitute out omega as 2 pi f. You will eventually get back this answer. Okay, so this is another different way too from finding the gradient, but provided you know how to change to the correct relation. Okay, so it's up to you to pick which one is more comfortable. Either way is accepted. All right.